In this video, we will find the local stiffness matrix in the global coordinate system. Let's review what we did in the last video. In the last video, we found the local stiffness matrix in the local coordinate system. We also found the transform matrix, which would transform us from the global coordinate system to the local coordinate system. And then we also found the unfortunately named transform of the transform matrix, which will go from the global coordinate system to the local coordinate system. Note that this matrix is a 2 by 2 matrix. This matrix is a 2 by 6 matrix, and this matrix is a 6 by 2 matrix. All right, now, to make things clear what these matrices do, I can define these four equations where if I multiply the local displacement vector by the transform of the transform matrix, I get the local displacement vector in the global coordinate system. Likewise, if I have the force vector in the local coordinate system transformed or multiplied by the transform of the transfer function, I get the force matrix, the force vector in the global coordinate system. If I want to go the other way, if I have the global vectors or the local vectors in the global coordinate system and I want to go to the local coordinate system, I multiply these vectors by the transform matrix itself. All right? So now I'm in a position with these four equations to derive the local stiffness matrix in the global coordinate system. So recall, the equation we're going to start with is the local force vector in the local coordinate system is equal to the local stiffness matrix times the local displacement vector in the local coordinate system. All right? The first thing I'm going to do is I'm going to multiply both sides of the equation by this vector. And I'm doing this, in this case, simply because I can, and it gets me where I want to go. And I'm going to multiply on the left side. So I'm going to get T star, the transform of that matrix, F hat, is equal to the transform matrix transformed times K hat times the displacement vector in the local coordinate system. All right. Now what I'm going to do is I'm going to substitute this expression using equation number 2. And I'm going to transform my U hat using equation number 3. So this, according to equation number 2, is equal to F, the force vector in the global coordinate system, is equal to T asterisk transformed times K hat, local coordinate system, times U hat. I'm using equation 3, so I'm going to replace U hat with the transform matrix times U in the global coordinate system. Now I have U in the global coordinate system. I have F in the global coordinate system, which means that I can define these three matrices multiplied together as simply my stiffness matrix in the global coordinate system. All right? So let's see what this looks like. I'm going to do all this math for you. I might make you do this matrix multiplication in an in-class exercise. And what we find is that K, the local stiffness matrix in the global coordinate system, is equal to T transformed times K hat times T, and we get this 6 by 6 matrix. And it should be a 6 by 6 matrix because note that this is a this is a 6 by 2 times, remember the k in the local is simply a 2 by 2, and this is a 2 by 6. The inner dimensions need to match. I got a 2 by 2 and a 2 by 2, and my outer dimensions end up being the dimensions of my new matrix, which is a 6 by 6. So we end up with a 6 by 6 matrix, which is a matrix I expect you to memorize. Before you have a panic attack, let's notice some structure to this matrix. First of all, if I split this matrix into 4 submatrices like this, you should notice that this matrix is the same as this matrix, and this matrix is the same as this matrix, and the only difference between these two matrices are this is the negative of this matrix. So if I want to label this matrix something like, oh, say, lambda, then I can simply say that my new K matrix is equal to a supermatrix made up of lambdas, lambdas, and negative lambdas, negative lambdas. Also notice that this structure is the same as this structure. Now, that means that instead of remembering, let's see, 6 times 6, 36 elements, now you're down to having to memorize 9 elements. Okay? But it gets easier than that, because if you notice, there's a certain symmetry to this structure. Notice that if I call this the x column, and I call this the y column, and I call this the z column, that the second element is cosine x, cosine x, cosine x, cosine y, cosine y, cosine y, cosine z, cosine z, cosine z. Also notice the rows. The first product in each member is all x's, all y's, and all z's. Okay? Lastly, remember that this matrix is going to get multiplied by the stiffness, by the displacement vector for each element. So remember that this column corresponds to U1, this corresponds to V1, this corresponds to W1, this column corresponds to U2, this column corresponds to V2, this column corresponds to W2. Likewise, you can think of each row as corresponding to U1, V1, W1, U2, V2, and W2. All right? And this will help us take the local stiffness matrix in the global coordinate system for this particular element, this particular bar element, and create the global stiffness matrix for the global truss system out of these individual local stiffness matrices. All right, that's enough for this video. We have enough material now that we can go ahead and do an example truss in 3D, and we'll do that in the next series of videos.